Curious, slightly hushed. Electricity will travel miles through certain materials in a fraction of a second, yet it stops dead the moment it touches a barrier. To understand why, we have to look at the paths we build for it. At its most basic level, an electrical circuit requires a power source, like a battery, and a continuous loop of wire. The red wire carries the positive charge, and the black wire carries the negative. Placed in the middle is our target device, an LED, or light-emitting diode. LEDs are strictly directional. They have a longer leg that must connect to the positive side of the battery, and a shorter leg for the negative. This directional requirement is called polarity. If you flip the LED around, it acts as a blockade and refuses to let the current pass. LEDs are highly efficient because they convert electricity directly into light. Older incandescent lamps work entirely differently. They force electricity through a thin wire filament, like tungsten, heating it up until it physically glows. If that tiny, fragile filament breaks, the path is destroyed. That continuous path is the only rule electricity strictly obeys. If you snip the wire, the LED immediately dies. A closed circuit is a continuous highway. Break the road, and the energy stops flowing entirely until we build a new bridge. If we bridge that snipped gap with a piece of copper wire, the light comes back on. At the atomic level, copper's structure allows free electrons to easily detach and glide from atom to atom. It acts as a perfect express highway for the current. Now, if we swap that copper wire for a strip of aluminum foil, the circuit still completes. The LED lights up, but the glow is noticeably dimmer. Both are metals, but aluminum has a higher electrical resistance. Resistance is a measure of how much a material opposes the flow of current. The internal structure of the aluminum creates more friction, causing the electrons to bounce around and lose momentum. The highway doesn't have to be made of metal. If you take an ordinary pencil and place the graphite core across the gap, the LED springs back to life. Materials like copper, aluminum, and graphite are known as conductors. A conductor is any material with low enough internal friction to let electricity pass through efficiently. If we place a rubber eraser, a plastic ruler, or a piece of glass into that same gap, the LED stays dark. The atomic structures of these materials hold tightly to their electrons. They act as solid, impenetrable walls. You don't even need a physical object to build one of these walls. If you pull the bare wire ends just a few millimeters apart, the current stops. That tiny gap of empty air completely blocks the flow of electrons. Air is a highly effective insulator. Rather than seeing this air gap as a problem, engineers use it to their advantage. By attaching a safety pin to one side of the gap, we can build a simple mechanical switch. Lifting the pin introduces the air gap into the circuit, turning the power off. Pressing the metal pin back down bridges the gap, allowing the current to resume, turning the power on. Insulators like air, rubber, and plastic are essential control mechanisms. They allow us to trap, direct, and turn power on and off at will. This control can easily be bypassed in unexpected ways. If you drop the live wires into a glass of perfectly pure water, nothing happens. Without any impurities, 100% pure water is an insulator. But the water from your tap or the sweat on your skin isn't pure. It is filled with dissolved minerals and salts. The moment those minerals enter the water, they align and create a jagged conductive highway for the electrons to cross. Touching live electronics with wet hands provides electricity with a low-resistance fast track directly through the moisture on your skin and into your body. A small battery delivers direct current, or DC, a mild flow of electrons moving in one continuous direction. The power grids that feed our wall outlets deliver alternating current, or AC. This current rapidly changes direction back and forth many times a second, and it travels at dangerously high voltages. When an AC shock hits the human body, it triggers severe muscle contractions, often forcing the victim's hands to physically grip the electrified object. The real danger of electricity lies in how everyday elements, like sweat, can hijack the human body's nervous system. To interact with this power safely, we design tools that combine both highways and walls into a single device. Look at a standard electrician's screwdriver or a heavy-duty power cable. The inner core is made of a dense conductor, like copper, to provide the high-speed highway. Wrapping that core is a thick layer of plastic or rubber, serving as the protective wall that safely isolates the current from our hands. This is why a frayed power cable is an immediate hazard. Even if your appliance still turns on, the protective wall has been breached. The high-speed highway is completely exposed to the outside world. We also build in fail-safes, like the third prong on a wall plug. That grounding prong serves as a dedicated emergency exit lane. If electricity escapes its path, the ground wire gives the rogue current a safer route straight into the earth, bypassing you entirely. Electricians master the physics of highways and walls to harness immense power. They turn raw, dangerous energy into a precise force while keeping the human body completely insulated from harm.